Hello everyone, I once again welcome you all to MSP lecture series on interpretive spectroscopy. In my previous lecture, I showed you how nicely phosphorus NMR can be used to detect or determine the number of epoxide groups present on carbon nanomaterials. It is very important, especially when you want to use pure nanomaterials for electronics and other semiconductor purposes. We have to ensure that there are no such parasites are sitting on graphene. From that point of view, this NMR spectroscopy, especially phosphorus NMR, comes very handy. So let me continue from where I had stopped. So now let's look into some important information regarding instrument operation as far as measurement of 30NP NMR spectra are concerned. So instrument operation will vary according to instrumentation and software available. It varies with different company instruments and the softwares employed there. However, there are a few important aspects to instrument operation relevant to 31P NMR one should know before they put their hands on instrument to measure 31P NMR spectra. The instrument probe, which excites nuclear spins and detects chemical shifts, must be set up appropriately for a 31P NMR experiment. This is very vital. Of course, these guidelines will be given. For an instrument with a multinuclear probe, it is a simple matter to access the NMR software and make the switch to a 31P experiment. Again, technician will guide you in this one. This will select the appropriate frequency for 31P. For an instrument which has separate probes for different nuclei, it is imperative that one be trained by an expert user in changing the probes in the spectrometer. So this is a typical NMR tube we are using, and this is a capillary tube containing 85% phosphoric acid, and this can be inserted and also we can measure. So for example here, before running the NMR experiment, consider whether the 31P spectrum should include coupling to protons or not, and you should remember the fact that 31P NMR spectra are typically reported with all protons decoupled. That's a default setup, and this is usually the default setting for 31P NMR experiment. To change the coupling setting, follow the instructions specific to your NMR instrument software, and chemical shifts in 31P NMR reported relative to 85% phosphoric acid. This must be an external standard due to high reactivity of phosphoric acid. So one method for standardizing an experiment uses a coaxial tube inserted into the sample NMR tube. I showed you in the last slide. So 85% phosphoric acid signal will appear as a part of the sample NMR spectrum and can thus be set to 0. So when you are measuring, you can also see signal due to phosphoric acid that you can set as 0, and accordingly with reference to that one, other chemical shifts can be automatically set. So this is the one as I mentioned. This is the capillary with phosphoric acid, a sealed capillary, and then this can be inserted nicely. So another way to reference an NMR spectrum is to use 85% phosphoric acid as a standard sample. These can be prepared in the laboratory or it can be purchased commercially. It's very easy to make provided we have a glass blower in our laboratory. To allow for long-term use, these samples are typically vacuum sealed. So what is the procedure for using a separate reference? So insert NMR sample tube into the spectrometer, tune the 31P probe and shim the magnetic field according to your individual instrument procedure. Remove NMR sample tube and insert phosphoric acid reference tube into spectrometer. Begin NMR experiment. As scans proceed, perform a Fourier transform and set the phosphorus signal to 0 ppm. Continue to reference spectrum until the shift stops changing and stop experiment, and remove phosphoric acid reference tube and insert NMR sample tube into spectrometer. Run NMR experiment without changing the reference of the spectrum. So this is how you can do alternately referencing phosphoric acid when you are measuring 31P NMR signals. And when we are using 31P NMR, it gives distinct sharp peaks that helps in identifying phosphorus containing new products and unreacted starting compounds and any other phosphorus impurities. So that is the advantage. And so 31P NMR is very simple technique for assigning sample purity readily. A clean 31P NMR spectrum does not necessarily suggest a pure compound, but it can tell you that it is free of phosphorus containing impurities. There may be other organic impurities are there, but that can not tell you any further information, but only if the spectrum is clean, it would indicate you definitely that there are no phosphorus impurities or any other minor products containing phosphorus. 31P NMR can also be used to determine the optical density of a chiral sample. Adding an enantiomer to the chiral mixture to form two different diastereomers will give rise to two unique chemical shifts in the 31P spectrum that probably at the end I will show you some examples. The ratio of these peaks can then be compared to determine the optical purity. So now let us look into a couple of more examples considering the reactions carried out with organometallic compounds with phosphorus containing compounds, especially phosphines. So 31P NMR can be used to monitor a reaction involving phosphorus compounds, no doubt in it. Consider the reaction of nickel cod twice is a nickel 0 compound with a slight excess of bisphosphine. So I am going to show the chemical reaction here. So this is the bisphosphine we are considering, and then when it is treated with nickel cod, this type of nickel 0 compound is formed with some interaction with orthocarbon present here. So still nickel is in 0 valence state and it's a 14 electron species, and then this can be readily monitored. How to monitor? It is very simple. Take the ligand and add that one to the nickel cod twice in an appropriate solvent, and then initially the signal, when you just begin the reaction, you can see the signal due to only phosphine here. With the time, for example, after 1 hour, you can see another peak started developing here, much downfield. This indicates the beginning of the formation of this compound, and then 2 hours, its gradually concentration of ligand is decreasing, and then this is slowly increasing. After 3 hours, you can see steadily it goes, and after 5 hours, it is completely reacted. And then if you just compare the integration, you know that you have used slight excess of this one, only the slight excess of bisphosphine used is left unreacted. That indicates the completion of the reaction. So that means by using variable time 31P NMR spectrum, you should be able to monitor the reaction in a continuous process and see you can stop as soon as you come to know that the reaction is completed. Not only in this reaction, when we are doing catalytic reactions also, we can look into the consequences that are observed on phosphorus in a catalytic reaction can also be very nicely followed using 31P NMR spectroscopy. So now one more interesting example is there here, that is with respect to cyclotriphosphazine. So indicate the number of isomers of cyclic compounds of formula and sketch the 31P NMR spectrum for each. So in this case some hint is given. Assume delta is much larger than J and JPH is small. If JPH is small, JPH can be ignored for phosphorus atoms which do not contain methyl groups. That means when you are writing like this, we have 2 methyl groups are there and 4 chloro groups are there. If we write all possible isomers, it so happens some of the phosphorus atoms will not be having chlorine. In that case, they will be little farther from the methyl groups. In that case, what happens? The pH can be ignored. That means we are plotting not decoupled one, we are plotting coupled one. What would happen if we take a decoupled one? It is straightforward. We have to identify how many different type of phosphorus environments are there in a given isomer. So here only 2 isomers are possible, either having both the methyl groups on one phosphorus or 2 methyl groups are distributed on 2 different phosphorus. Since only we have 2, so either we can have this possibility or we can have this possibility. And in this one, if you are considering protons also, it would resemble A2MX6 spin system, or here what happens, it would be AM2X3 spin system. So that means let us look into how the NMR is going to look like. Ignore AX coupling in both the cases. So AX coupling, because A and X are far apart, you can ignore the coupling. Only you can see the direct coupling. So here for example it is a 2-bond pH coupling can be considered, and rest of the long range coupling can be ignored. Now if we just look into this one, these two are identical and this is different. So that means basically when we look into, if I say PA here and this is M and this is X here, if we look into delta A, first it will be split into a doublet. This is 1 to 2J PP coupling, PA, PB, and then here this is coupled with 6 of them are there. So if 6 of them are equally coupled, so you should get 6 means 7 lines, n plus 1 line should be there because I equals half. So what you get is 1, 2, 3, 4, 5, 6, 7. Similarly here also 1, 2, 3, 4, 5, 6, 7. So something like this we get it. And for PM, so this will be coupled with this one into triplet, and then each triplet will be again a septate here. So you can see this one. So this is the NMR spectrum for this one, and of course here you can also ignore the coupling in this case, but anyway I have considered both small range coupling. Then if you go for this one here, again here these two are identical. If you put A, or if I put A here, this is M and this is X. I will show you spectrum here. You can see A2MX6 system. As I said, these two do not show proton coupling. I showed you there, but it will be something like this. Okay, it simply shows a doublet coupled with this one we are seeing here. This, if you say A and this is M, this is delta A, and then this is for delta PM. So here first it shows a triplet and each line will be split, and what you see here, this is your PH coupling. Okay, so 2-bond, 1 to 2-bond coupling, and this is 1:2:1 triplet, and then we have each one is a septate. So an AM to X3 you can see here, and this triplet is for this one. If I say A, M and X, so A will be delta PA will be a triplet here, and then this coupling is 2JPP. So you are not seeing long range. If you see long range again, this will show a septate again. So now the other one, since both are identical, here not we are going to get septate, we are going to only quadrate. So each line in this one. So if you take these two are coupled with this one to a doublet, something like this, and each doublet now, since this is identical with this one, only a quadrate will be seen. You see quadrate, and this is JPH coupling. So this is how you can interpret and you can identify if both the isomers are present in say 1:1 ratio or 1:3 ratio or whatever. So we should be able to clearly distinguish them by using simply phosphorus NMR spectrum. Now let us look into another interesting compound here, the reaction of zirconium tetrachloride DPPE. DPPE is bis-diphenyl phosphinoethane with magnesium, dimethyl magnesium here, gives a compound of this type where we have 4 methyl groups are there and DPPE is there acting as a bidentate ligand. So NMR spectra indicate that all methyl groups are equivalent. Draw octahedral and trigonal prism structures for the complex and show how the conclusion from NMR supports the trigonal prism assignment. So this is very simple, and it shows that this compound with coordination number 6 can have both octahedral geometry and trigonal prismatic geometry. So this is octahedral geometry here, and 4 in the plane and 2 axial, and also this octahedral compound geometry is also known as trigonal antiprismatic geometry. Trigonal antiprismatic geometry. So in this one, if you try to arrange 4 methyl groups and bridging diphosphine, you cannot really come up with a isomeric form that has all 4 methyl groups equivalent. For example, to make them equivalent, I have to put all of them in the plane. When I put all of them in the plane, what happens? These two vertices will be far apart. It's very difficult to fix bis diphenyl phosphonethane in this way because the ring size is not sufficient. So it can either go here. When it goes here, again it will not be very symmetric. So from that point of view, what happens? It is ruled out. On the other hand, trigonal prismatic geometry, okay, all four can be, for example, this is a trigonal prismatic geometry, that is trigonal antiprism. And of course, why you can say prism is something like this, you can see. And then if I turn something like this, then it becomes trigonal antiprism, staggered trigonal prism. So now with this one, what happens? Let us say it has four rectangular faces are there. If four rectangular faces, let us say if I can put here very conveniently 1, 2, 3, 4 methyl groups are there, and then if it is the bisphosphine, I can fix in this way. If I fix this way, what happens? Now we can see if I cut a axis here, this can divide, and now both of them can be magnetic equivalent, or if I do some rotation from this one, C2 axis of rotation, they will be identical. So that means with trigonal prismatic geometry, with this kind of conformation, what happens? All the four will be identical. That means when we look into 13C NMR spectrum of this compound, it shows only one signal for all four carbon atoms. That clearly indicates that this compound has trigonal prismatic geometry with all methyl groups are in one plane, something like this. So we can conclude without any problem. So that means whatever the statement that is made in the question can be fulfilled by putting this kind of geometry here. And then of course these two phosphorus are identical. If you look into phosphorus NMR, it shows only one signal. And if you look into 13C NMR, and if you focus our attention to methyl groups, we will get only one signal. So I have shown here, for example, here it has a different one, and two type of, we will come back to axial and equatorial. Again, same thing is true here. And whereas here trigonal prismatic, either you can see here or here, they look identical. And then you can see what I showed through these models. So this is how, once again, NMR can be used to understand the geometry and the preference of groups very readily by simply looking into the corresponding NMR spectra. So now I have another interesting reaction here. This is with tris-trimethyl phosphine chloroiridium. So when the 4-coordinate square planar complex IRCl-PME3 thrice, where PME3 is trimethyl phosphine, you all know, reacts with chlorine, two 6-coordinate products of formula IRCl3-PME thrice are formed. So that means we are adding oxidatively chlorine to iridium-1 to form iridium-3 compound having 6 coordination. From square planar 16 electron, it forms a octahedral 18 electron complex. Iridium-1 changes from +1 to iridium +3. So 31P NMR spectra indicate one phosphorus involvement in one of these isomers and two in the other. What isomers are possible? So when you look into MA3B3 type system, so we have MA3B3 system, and of course when we have MA3B3 system and when we have MA4B2 system, so we know that two isomers are possible in case of octahedral compounds. Of course here coordination number is 6. So in case of this one, we get facial and meridional isomers, whereas in this case we get cis and trans isomers. So since after oxidation addition, we are getting MA3B3 possible isomers are facial and meridional. So that means here, let's assume A is Cl and B is PME3. So now we have two isomers are there. You can clearly distinguish them. In this one, all A's are on one phase, so that all trimethyl phosphines are one phase and all chlorines are in another phase. So this is a facial isomer and this is meridional. So we have trans as well as cis. So in this case what happens, if we just look into, we have two different type of phosphorus atoms are there, and then if you look into the spectrum here, this will give a triplet, and then whereas these two will show a doublet. So we get a pattern something like this, whereas in this one we get a singlet. So that means what it says, 31p NMR spectrum indicate one element in one of these isomers, this is facial, and two in the other. Two will be in case of meridional, one doublet and a triplet. So this is how we can identify simply by not even plotting, simply by looking into the number of signals that are present. Of course, when we look into signals, we know that one has to be a doublet and one has to be a triplet. And then this doublet intensity should be, it should correspond to 2 and it should correspond to 1. Okay, so now there are a number of advantages for using 31p NMR for reaction monitoring when available as compared to 1H NMR. It's very simple. You saw with several examples how simple it is to use phosphorus NMR as a tool for our advantage to understand the type of reaction we are doing and how to change the course of the reaction and all other details. Another advantage with phosphorus NMR spectroscopy is we don't need a deuterated solvent, which simplifies the sample preparation and save time and resources. That means when we are doing a reaction, say continuous reaction, especially in homogeneous catalysis, say instead of doing batch reaction, we can take at regular intervals a liquid and they can look into, if we have provided we have phosphorus moieties in it, we can readily monitor without going to expensive deuterated solvents. So 31p NMR spectrum is simple and can be analyzed very quickly, much easier. So the corresponding 1H NMR spectra for the above reaction would include a number of overlapping peaks for the two phosphorus species as well as peaks for both free and bound cyclooctadiene ligand. So that means it is very simple here. Instead of going for 1H, one can conveniently go for phosphorus 31p NMR spectra. So purification of product is also easy. And that means how we can purify this information also comes from spectroscopy. 31p NMR does not eliminate need for 1H NMR characterization, as impurities lacking phosphorus will not appear in 31p experiment. So basically what happens, 31p NMR does not eliminate the need for 1H NMR characterization, but as far as 31p NMR is concerned, if the spectrum is clean, that indicates that there are no phosphorus containing minor products or impurities, but on the other hand there can be something else. So that means one should also confirm purity by going for 1H NMR or other nuclei NMR as well. So however, at the completion of the reaction, both the crude and purified products can be easily analyzed by both 1H NMR and 31p NMR spectroscopy. So let me stop and continue in my next lecture about many other NMR active nuclei, for example 19F, 14N, 15N and other nuclei such as even boron. So let's continue a discussion on spectroscopy, especially NMR spectroscopy in my next lecture. Until then, have an excellent time. Thank you.